Okay, so in this video, I just wanted to get some more practice with derivatives because if you don't practice derivatives, it's just better to practice derivatives so that it comes more naturally when you're solving these problems. And even when you run into some word problems, you can identify patterns more quickly. So the first problem I want to look at is just find the slope of the tangent to f of x equals 3x squared minus 5x plus 7 at x equals 1. Okay, so we know that the slope of the tangent is just what the derivative is equal to. So we have the function and we just want to take the derivative of that function. If my pen will work. There we go. So we want to take the derivative of that function. That's going to be, do the power rule for this term, and then same thing for this term, and then we know that the derivative of a constant is 0, so we're just left with 6x minus 5. And we want to evaluate this at x equals 1. So we get that the slope of the tangent is just equal to 1. Simple enough. Okay. Before we actually move on to some more practice problems, I want to go over some identities that you'll want to memorize to make some of these next problems go a lot faster. And the first one is taking the derivative of sine of x, or sine. So the derivative of sine is cosine of x. And if we take the derivative of cosine, we get minus sine. And then if we take the derivative of tangent x, we get secant squared x. And there are proofs for all these identities. If you just search up online, they're not too hard to understand. Um, but if you memorize it, you'll be fine. So the derivative of cotangent will be negative cosecant squared x. And then the derivative of secant will be secant x tangent x. And the derivative of cosecant will be minus cosecant x. Oh, sorry, it's kind of sloppy. Cotangent x. And then there's only a couple more. I know this seems like a lot, but if you just spend 10 to 20 minutes memorizing this, they'll become like second nature to you. So the derivative of e dx, probably the most simple derivative of all time, or is the most simple derivative, is just e to the x. Some more complicated identities. The derivative of natural log of x is 1 over x. The derivative of a to the x. So if we have a number raised to the variable, we can't use the power rule here because it's different, even though it kind of looks the same. Is this going to be the natural log of a times a to the x? And then finally, the last two, we have dx of inverse sine. And that's going to be 1 over, oh, it stopped working, the square root of 1 minus x squared. And finally, if we take the derivative of arctan, or inverse tangent, I'm just going to write it this way so you're familiar with both ways of writing inverse trig functions, is equal to 1 over 1 plus x squared. Yeah, so those are some of the identities that are going to be pretty beneficial to solving some derivative problems. So let's take a look at this next example where we have g of x is equal to 1 over x minus 4 tangent x plus 4x plus 2 times the square root of x. Okay, so if we want to take the derivative of this, well, if we want to take the derivative of 1 over x, we're going to need to bring the exponents at the top and then use the power rule, so it's going to be minus x to the negative 2. Then now we run into one of our identity problems, so we have the derivative of 4 tangent x. The 4 doesn't affect anything, but we know that derivative of tangent is secant squared x. Oops. Secant squared x. And then finally, we look at the plus 4x. We can just turn that into 4 because of power rule. And then lastly, we have 2 times the square root of x. So here we're going to change the exponent. We're just going to rewrite it to 1/2. Bring the exponent down, the 1/2 and the 2 become 1, and then we're going to decrement by 1. So we're left with x to the negative 1/2. And so that's our final answer for that problem. But we can simplify it by making sure we don't have any negative exponents. I know the AP test doesn't like that. I think it's fine, but if you want to be safe, you can bring those exponents down. Oh, my pen stopped working again. There we go. Secant squared x plus 4 plus, and then we have 1 over, you can write it like that. Actually, you don't want to write it like that because you don't really, well, it's fine for the purposes of this video. We're really just focusing on getting our derivatives fine-tuned. Okay, so I like how that's going, and I just want to let's do one more example. Yeah, we'll do one more. So, example 3. This is another word problem. I'm not going to write it out. I'll just talk about it. So let's say we have the function f of x equals x plus sine of x. And we want to find all value of x on the interval 0 to 2 pi, where we have a horizontal tangent. Now, I want you to stop for a moment and think about what a horizontal tangent means. So if we have a curve, let's just say it looks something like that. A horizontal tangent occurs here, here, basically anywhere where, we can draw a flat line across. And what this means in terms of our derivative is we're going to look for where our slope at a point, slope of the curve, is 0. So we're going to take the derivative of our function right here, and we're going to see that that becomes to 1 plus, and the derivative of sine is cosine. And then we're going to want to set this to equal to 0 because we're looking for when that slope is 0. Our horizontal tangents are 0. So we get negative 1 is equal to cosine, and we can inverse both sides, and we can get that x is equal to inverse cosine of negative 1. And what this is saying is what values of x will, or what values can we plug into cosine that will give us a negative 1 for x. And if you remember unit circle, the only value where we can get a negative 1 from cosine is right here, and that angle is pi radians. So x will be equal to pi, and on our interval, that's the only value for x where f of x has a horizontal tangent. And so that's going to wrap up this video.